much for having me here. So I think this is a little bit different than the talks we've heard so far. So please bear with me and I don't know, just interrupt me during the talk or anything. Like, I'm happy to answer questions during the talk as well, so we don't lose too many people. So today I'll be telling you a little bit about a series of papers that we wrote in collaboration with very brilliant collaborators, Scott Collier, Lawrence Eberhard, and Victor Rodriguez. I think Lawrence should be in London. He's on his way here. So very good. So zooming out, just so you really have a takeaway message, is we had lots of beautiful talks about ADS CFT. So, but we're living in a space-time that's asymptotically de Sitter. And there's a dearth of controllable models of quantum gravity in expanding spacetimes. And I think it's pretty fair to say is that there's no unifying picture of de Sitter quantum gravity that comes close in scope or rigor to anything like ADS CFT. And I think basically this knowledge that we have this expanding spacetime, that we need to understand this, and combined with the lack of any unifying picture, is what really motivated in the last few years a lot of us to go to low space-time dimension. By low space-time dimension, I mean 2 space-time dimension and 3 space-time dimension. So we are not neglecting 4-dimensional real world, but we are just going down in dimension, trying to get as much insight as possible, and then trying to use this insight that we got in low dimensions to learn something about the 4-dimensional world. And in particular, we are hoping to really get a controlled setup in which we can study, for example, a microscopic model for de Sitter quantum gravity. And in this talk, what I'll focus on is 3-dimensional de Sitter, so 3 space-time dimension, 2 space, 2 1 time. And I'll tell you a little bit about this concept of canonical quantization, so we will build a Hilbert space. I'll then tell you a little bit about the wave function, and I know many of you will not come from this, so but bear with me in this wave function discussion. So this is a little bit different than maybe this Hodel-Hawking wave function that you've heard so far. I'll then tell you how we are tying this this 3D de Sitter world to a string theory, and the string theory is known as we call this string theory the complex Liouville string. I'll then tell you how we are tying this string theory to a matrix integral, and this matrix integral is then going to give us all the observables in this theory. And then so I'll go to a Euclidean picture, or a static patch de Sitter perspective. So static patch perspective is really us. So we as an observer are surrounded by a cosmological horizon. Gibbons and Hawking told us that there's an entropy associated to this horizon. And I will tell you how this entropy is talking to any of those string theories and matrix models. Very good. So let's just jump into it, and please interrupt me. I know this is a little bit different than what we've heard so far. So the canonical quantization of dS3. Right. So we start with 3D Einstein gravity with positive cosmological constant. So this is this Lorentzian action over here, where notably lambda here is positive. So lambda is related to the de Sitter length as in this following way in 3 dimensions. So this theory with lambda positive is loosely related to SL2C trans-Simon theory. So this is different than lambda negative. Lambda negative, this is SL2R times SL2R. This is lambda positive, so it's SL2C trans-Simon theory. My saying loosely here is just that there are important caveats when we are trying to relate this metric formalism to the Chern-Simons formalism. Notably, for example, the invertibility of the metric, the global structure SL2C, PSL2C, and so on and so forth. Large diffeos that are gauged in the gravity theory and not in the Chern-Simons theory. So you need to be very careful if you're jumping between metric formalism and Chern-Simons formalism. Okay, but so we will now take some slice. So some slice of this 3D de Sitter, which is a 2-dimensional surface. And I call this 2-dimensional surface, this initial value surface sigma gn. I call this 2-dimensional surface sigma gn. And for the sake of this talk, I will always push this sigma gn to be squared plus, so be the infinite future. And moreover, in this talk, I will always assume that my sigma gn is compact and hyperbolic. So I'll always assume that 2g minus 2 plus n is bigger than 0. So g is the genus, n is the number of punctures. So in particular, I will never let sigma gn be the sphere, or the torus without any punctures. Right, so then we will take the phase space of this initial value surface sigma gn, which consists of the metric and the extrinsic curvature. And then, as in quantum mechanics, we will choose a polarization. And for the choice for us is that we will make the wave function depending on the metric only. And moreover, what we need to impose are these two conditions, like this etheric gravity. So we need to impose the DeWitt equation, which is nothing else than this Hamiltonian constraint, and the momentum constraints over here. And in particular, these two conditions are going to make my wave function to be a function of this quotient space. So from this, with the DeWitt equation, I get like this two, and the momentum condition, I get this diff times val. And now 3D comes as a savior, because in this case, where the initial value surface is two-dimensional, this quotient space is nothing else than the moduli space of this surface sigma gn. Very good. So now, okay, depending on how we are looking at this quantization, we need to take into consideration, as I mentioned before, that if you're going to do Chern-Simons formalism, you're not gauging the large diffeomorphisms, you're only gauging small ones. So to really relate the gravity theory to the Chern-Simons formalism, we need to gauge the mapping class group, which is nothing else than this ratio between large and small diffeos. But then in the end, so my Hilbert space is going to consist of functions, well, sections, but okay, whatever, of functions of this moduli space mgn of this surface. Like, so far so good. But then if you really properly go through this derivation, so go impose this momentum and this Hamilton constraint and this wave function psi, or if you just use some DSCFD jargon that you know in the back of your head, you're going to find that like these conditions are really some Virasoro word identities. And from these Virasoro word identities, you can read off that your wave function psi transforms like a CFD correlation function with a central charge and a specific conformal dimension. And the central charge that you can read off from these Virasoro word identities is 13 plus something imaginary. So here, the tilde really means that there in principle could be further imaginary corrections. But the one loop piece, which is the 13, is the unique real part of this central charge. And the conformal dimensions, which are the combination of left times right movers here, they're given, they're in this form 1 plus IR. So in particular, they're in the principal series representation of SL2C. Now this intermediate part over here, this is DSCFD, so which relates the conformal dimension to the mass. And so if you want this square root, so this ingredient of this number inside the square root to be negative, so that this is purely imaginary, you can read off that m is of the order 1 over L de Sitter. So these are heavy particles. Just hold on a second. So in principle, what we're talking about, we have some punctures, and these punctures extend to some Wilson lines of some non-dynamical particle in the bulk. So this is pure 3D gravity, so there's nothing dynamical. There's a punctures that extend in the Wilson lines in the bulk. Yes? How do you get? Oh yeah. So this you basically like read off from this. Like if you look at the Chern-Simons formalism, and then you impose this constraint. So if you really properly go through this imposing this condition, you can just read off the central charge. No. Right. Well, I mean that could be further corrections. So this is the tilde. So there could be further like G Newton over L corrections, but that are all imaginary. Very good. And okay. So for the sake of this talk, and this will pop up later, it's often convenient to parameterize the central charge using this B parameter here. And if you compare these two different things, so these two things, then in this parameterization, B squared has to be purely imaginary. So this will just be useful later. Very good. So we have a wave function. The other thing that we need is some sort of inner product. And the inner product that we will take is nothing, it's just like, okay, some pretty standard inner product. So we throw in psi and psi prime, which are living both in this Hilbert space HGN. And then we're considering psi star, and we're dotting this with psi prime. So this you can forget about it for now. If you're interested in this prefactor, which is actually important for us, come ask me later. For now, this is just a normalization. But now, in particular, because we are dotting psi star with psi, the imaginary pieces drop out. And so the central charge of this object in here is like C plus C star, which is 26. Perfect. So this is perfectly well something we can put into this moduli space integral. And the total conformal dimension of this thing over here is 2. Okay, and you can also see that it's spanless. So in principle, like this object over here, like the right-hand side of, I think for you the right-hand side, yes, the right-hand side, like this side over here, is nothing else than a string theory path integral. Very good. So now let's go into like, we have the wave function, like let's look at what kind of wave function does this state describe. So we consider the following universe. So remember that I told you that my scribe plus, which is my surface sigma gn, is compact and hyperbolic. If I'm imposing that, this scribe plus is compact and hyperbolic, so in particular this thing over here has richest scalar -2. But if I want this whole thing to solve this 3D and Hilbert equation with positive cosmological constant, then what I need to put here is a sinh. So if you know global de Sitter, in global de Sitter, this sinh is a cosh. And then it has this like this hyperboloid structure. In this case, because indeed this sigma gn is compact and hyperbolic, I need to put this sinh over here. And in particular, what this means is that this spacetime has a singularity at t equal to 0. So this spacetime has a bulk singularity at the point t is equal to 0. So this is a Milnor type singularity. And this is a very interesting point, but I think for the sake of this talk, I will not have time to explain this in detail, is that this wave function now differs significantly from the Hartle-Hawking now boundary discussion. But for us, it seemed to be the suitable object to consider as three-dimensional de Sitter. Very good. So now, given this boundary condition, so given the fact that we have this boundary condition at square plus and this boundary condition here at t is equal to 0, which in the Chern-Simons formalism means that A is equal to A bar, so you have the gauge field A. And so to have like a vanishing Zweibein here, you need that the gauge field A is equal to A bar. So given these boundary conditions, the unique wave function, at least as far as we know, is given by this Liouville correlator. So I'll explain in a few seconds what exactly Liouville theory is, although I think there are some experts in the room that know what Liouville theory is better than me. So the wave function for this genus G and number n of punctures is given by these correlation functions. So V over here are vertex operators in this Liouville theory that I will explain in a second. And I will label the conformal dimensions by some p's, which are called the momenta. And the p's are related to the conformal dimension this following way. So remember that I said my delta from the canonical quantization was of the form 1 plus IR, so it was in the principal series. The central charge was 13 plus something imaginary. So that in particular implies that the pi squared is purely imaginary. Very good. And this wave function now has a bunch of very desirable properties. So this wave function, just given that it's Liouville theory, it factorizes under the generations of square plus. It is crossing symmetric in and on itself, so I don't need to like summarize any topologies. I don't need to do any fancy things for this wave function. This is crossing symmetric in and on itself. And it is a normalizable wave function. And to that we will also get in a second. Very good. So very good. And now what we can form are observables. So what are the observables in the game? The observables in the game are cosmological correlators. So this thing here is what Malasena in 2002 called cosmological correlators. For the sake of this talk, this paper, we called them integrated cosmological correlators just because there's a lot of confusion in literature that didn't integrate the cosmological correlators. But if you want to have gauge invariant observables, you better integrate them. And so these are just the gauge invariant observables in this game. And so you take a bunch of like operators, and then you put them into this integral where you integrate over all the metrics on square plus with your wave function. Now taking the wave function to be the Liouville correlator, this object over here is nothing else, just like carefully written out. So we have the metric when we just carefully divide by diff times val. This is just like, I didn't put this here just like for the sake of convenience. But in principle, we would have to like really divide by diff times val, and then we put in the wave function. Now the reason why I don't put any extra O's is because these are really massive particles that backreact and modify my wave function. So I'm just doing the de Sitter quantum gravity, not the de Sitter QFD on a fixed, on a de Sitter background. This is not rigid de Sitter. This is the de Sitter quantum gravity. Very good. And if you if some people are very happy with me summing over all genera, some people are not. I'll give you a motivation afterwards for why this is very obvious in our game. Or let me give it to you already now, kind of. So the reason why we're summing over all genera over here is because we're going to relate this expression now here, which are these cosmological correlators, to some string amplitudes in some string theory. And the string theory we're going to relate to a matrix integral. And in the matrix integral, we are not asked, we have to sum over all genera. So the matrix integral backwards tells us we need to sum over all the genera here. So now what I'm going to do now, and how much time do I have left? Perfect. So in the next 15 minutes, I'm going to tell you how we're taking this cosmological correlators over here that we got from a canonical quantization of 3D de Sitter gravity. How we are relating this object over here to string amplitudes AGN of a two-dimensional string theory, and how this two-dimensional string theory is nothing else than the matrix integral. So are there questions here? This is a lot of things. Oh, this is just because I'm integrating all the matrix here. That's what I mean, yes. Very good. Good. So let's look at these AGNs. So far, this is a bit mysterious object. Now let me give you the AGNs for arbitrary G and N. So, and I'm going to give you the AGNs through this string theory that's called the complex Liouville string. So the complex Liouville string is the following 2D string theory. It takes a Liouville CFT. So Liouville CFT is a two-dimensional CFT. It's a non-compact CFT. That means it has a continuous spectrum and a non-normalizable vacuum. And so I'm taking this Liouville CFT to have central charge 13 plus I times lambda, lambda being any real number. And I'm pairing it with its cousin, which is its complex conjugate. So in such a way that the total central charge of these two things adds up to 26. And so it's killed by the BC ghost. This is just a 2D string theory. And now, as a 2D string theory, what I need to impose is the mass shell condition. So I need to impose the conformal dimension of this theory, of the vertex operator of this theory, the conformal dimension of the vertex operator of this string theory add up to 1. And that in particular implies, in terms of the momenta of these vertex operators, that they are tied in the following way. And this is a string theory. If you look at H plus H tilde, so the left and the right movers, it's going to tell you that the conformal dimension is 1 plus IR. But let me just stress out here. So let me just make this point clear. Here, now I'm taking a string theory. So I'm just imposing the mass shell condition on a string theory. And imposing the mass shell condition on this string theory gives me delta is equal to 1 plus IR. This is nice, but previously the delta is equal to 1 plus IR I got from a canonical quantization. So they happen to be the same, but the way that we got them are different. So, and the observables in the string theory are the string amplitudes. String amplitudes are the following object. So you take the correlation function of this theory, take the correlation function of this theory, and you put in the BC ghosts. And the fact that there's an absolute value squared is because I have Liouville CFT with Liouville CFT star. So that gives me this absolute value squared here. But now this is nothing else than what we found previously as a unique solution of the wave function. So this AGN is nothing else than the integrated cosmological correlator of 3D de Sitter quantum gravity. And so I have my AGNs now for arbitrary. I have my AGNs defined as string amplitudes of some two-dimensional string theory. Now this is wonderful. And computationally, I can look at the string amplitudes for some low G and N. So for like the 4-punctured sphere, for the 1-punctured torus, I can put this on the computer and calculate this. This is really because these integrals are absolutely convergent integrals. This is because this is Liouville CFT, and in this Liouville CFT, these things are absolutely convergent. But it's still hard. To really push this to arbitrary G and N is really, really hard. However, the savior is a matrix integral. So, and let me just point this out. So what I mean by a matrix integral here is a double-scaled matrix integral. So this is notably different than like the 80s, 90s discussion of a matrix integral. So double-scaled for me is a limit in which I already took the size of the matrix to infinity and zoomed into a specific region of its eigenvalue distribution. So I give you this finite n matrix integral over here, but just to tell you that this is where it originally came from. But I don't have access to this finite n matrix integral. I just know that something of this sort was the starting point. So, but the starting point indeed was like not a single matrix integral, but a 2 matrix integral. And the two matrix integral with two Hermitian matrices, M1 and M2. So then I take this Hermitian matrices, M1 and M2, and I have a potential for M1 and a potential for M2, and I have this interaction. And observables in the matrix integral are resolvents. Resolvents are given by this trace. So I could look at resolvents for one matrix. I could look at the resolvent of the other matrix. If there's no superscript, it means the resolvent of one matrix, but this is an arbitrary choice. So, and then in this double scaling limit, so in this limit in which I take my size of the matrix to infinity and I zoom into a specific region of the eigenvalue distribution, these products of these resolvents have this genus expansion over here. And what I'm after now is I'm after trying to find these coefficients RGNs. So the RGNs follow from a sort of loop equation, which is now, or which I will introduce as a topological recursion. So let's take this a little bit of a step back again. So let's look at this resolvent again. So what you can see here immediately, so in principle there's an identity here. So whenever x hits one of the eigenvalues of m, this thing is going to have a pole. If I take the size of this matrix to infinity, these poles are going to smear out and going to form a branch cut. So my resolvent in principle is a multi-valued function that's going to have branch cuts whenever it's going to hit some of the eigenvalues of this matrix. So because I don't like multi-valued functions, what I'm going to introduce is a Riemann surface on which my resolvent is going to be single-valued. And this Riemann surface on which the resolvent is single-valued, that's called the spectral curve. So, and for the specific, for the complex Lover string, we found that the correct spectral curve is parameterized by these two functions, x of z and y of z. So it's these two trigonometric functions. And just if this was a bit too abstract for you, one thing that we can get from the spectral curve is the eigenvalue distribution. This is because the spectral curve is really related to the resolvent, and from the discontinuity of the resolvent, I guess many of you might know is that from there we can get the eigenvalue distribution. So looking at the discontinuity of the resolvent, we can get the eigenvalue distribution. So for example, this is the eigenvalue distribution of one of the matrices. If you look at the discontinuity of y of z, you will get the eigenvalue distribution of the second matrix, which is just the mirror symmetric expression over here. So, and it takes the following form. So the 2 is just a normalization. So we start at 2, it goes up, and then it goes down. And then something really, really bad happens over here because the eigenvalue distribution should not be negative. But I will get back to this later. Very good. So, and now we are done, because now we plug this into what's called topological recursion. So we plug the spectral curve into the topological recursion, which takes starting point omega 0,1 and omega 0,2. So genus 0, one puncture, and this is defined in this following way. Omega 0,2 we can borrow from this result of Einard and Orentine because it's always the same for every Hermitian matrix integral. And then the topological recursion is a recursion in G and N and gives us recursively the omega GNs. So these things over here. And the omega GNs are related to the RGNs, which are these coefficients of the product of the resolvents. So if we have all the RGNs, we have solved the matrix integral. And now, okay, finally, there's a relation between the omega GNs and the AGNs. And so once we have all the omega GNs, we have all the AGNs. So we can basically find the string amplitudes, which are nothing else than the cosmological correlators from a topological recursion recursively. So, and what was really hard before now becomes a recursive problem. So, and in particular, you can even develop some kind of Feynman rules to really get these cosmological correlates for arbitrary G and N. So here, I just for simplicity, I wrote down A04, but you can go to like A105 if you so want to. So I think in the paper, even we report about like A52 or something like that. So it's pretty straightforward. So it takes this form, but I think for the sake of time, I will not explain you the details, but please just like come and ask me. So actually, how much time do I have? Perfect, yes, perfect, that's perfect. So, but okay, so are there questions? Because now we're gonna switch gears a little bit from a very like global perspective, so like integrated cosmological correlators, to a more like static patch de Sitter perspective. Yes? Oh, it's you need to take the residue, evaluate it at some branch points. We have it in the paper. So I mean, it's, yeah. Do you know the work of Salzschenker-Stanford? It doesn't, okay. It's a known relation. It's a known relation. So, okay. So now let's switch gears then, and let's go from like this square plus, which was in this like global de Sitter-Penrose diagram over here, to us. We are having our little world line over here, and then we have the event horizon that's surrounding us because of the expansion of spacetime. And now, notably, if you Wick rotate static global patch de Sitter Euclidean signature, you're getting the sphere. So this is this sphere over here. Very good. In Gibbons and Hawking, much inspired by the results of black holes, conjectured that the cosmological horizon encodes an entropy. And this entropy is, according to Gibbons and Hawking, given by the sphere partition function. So in the case of 3D de Sitter, it's given by the 3-sphere partition function. 4D de Sitter is given by the 4-sphere partition function. So basically, you kind of like the Wick rotation of the static patched Euclidean signature. So you take this gravitational path integral, which is a Euclidean gravitational path integral on a 3-sphere here, and then you hit it with the logarithm. So this is just, in principle, this is like Euclidean thermodynamics. It's just in the Sitter space, the energy is 0 because the Cauchy slices are compact. But in principle, if you add some E over T over here, then this is just Euclidean thermodynamics. So this gravitational path integral over here was obtained to one loop order in this paper over here from the Euclidean Einstein-Hill production. And what you find is that this hitting it with the logarithm, you get these contributions. So this first part over here, pi L de Sitter over 2G, is nothing else than the area of this horizon. So you have this horizon over here. So this horizon. So the area of this horizon you calculate to be is given by 2 pi L de Sitter. Then you divide by 4G newtons. So this is like the standard, like in principle, black hole area of 4G, which is in this case true as well. So, and this leading piece is the fact that this gravitational path integral on the sphere really evaluated to leading order to area of 4G. That's really what like pushed the Gibbons and Hawking conjecture. Then the next contribution that you get from this gravitational path integral over here is like a log with a coefficient that in dS3 is 3. So it's related to the dimension of the symmetry group, so SO4, sorry, the dimension of the symmetry group of the sphere. So for the 3-sphere, it's SO4. For the 4-sphere, it's SO5. So it changes depending on which dimension you're living in. In 3D de Sitter, it's 3. And then you get another log correction. And then you get this kind of infamous phase over here, which is the Gibbons-Hawking-Perry-Polchinski phase, which you get because the Euclidean gravitational path integral is Gaussian unsuppressed. So there's this conformal mode problem, that Euclidean gravity, in principle, the conformal mode is Gaussian unsuppressed. And how Polchinski and Gibbons-Hawking-Perry solved this is by Wick rotating the field. And then you end up with another problem, and I'm happy to explain this in more detail, but this other problem is that you rotated a few modes too much, and a few modes too much, then you needed to Wick rotate back. The number of modes that you Wick rotated too much in 3D de Sitter, sorry, for the 3D path integral is 5. So that's this 5 over here. The 5 doesn't matter. In principle, this is an I. So 5 pi I over 2 is pi I over 2, like, I mean, so it's I. And okay, then you can get further corrections over here. Okay, so this is a gravity slide. But why am I telling you about this gravity slide? Before I told you about the matrix integral. Now let's go find these numbers from a matrix integral. So, okay, so I had this matrix integral. I had a matrix integral, though, which was not a finite n matrix integral, but I had a double-scaled matrix integral. So I took the size of this matrix n to infinity. So a priori, like if I would tell you like how many degrees of freedom like are left in this matrix integral, you would tell me, oh, it's infinity because I took n to infinity. But now let's look again at like the eigenvalue distribution that I had before. So, and this eigenvalue distribution had this following form. So it started somewhere, it went up, and then it went down, and then it had a bad regime in which it went negative. It's bad. Eigenvalue distribution should not be negative. Let's close our eyes, and I tell you now, like we have no a priori reason why this is okay. This is just seemed to work. It would really need a better explanation. So let's just stop here. Let's just assume all there is in this matrix integral is this blue shaded region. If you're really careful, like you can actually find that at this point here, non-perturbative effects start playing a role. So far, everything was perturbative. At this stage, actually, when the eigenvalue distribution hits this 0, that's the location in which non-perturbative effects have to start taking into consideration. So at this stage, something has to happen, which would render this eigenvalue distribution non-negative, but we don't know what exactly. But let's just close our eyes for now and just assume that everything that's left in this matrix is this blue shaded region. And let's take the eigenvalue distribution and integrate it from 2 to this point x naught. So the eigenvalue distribution we had, and we can perform this integral exactly. So this tilde over here just means that I forgot some pi's, but we can do this integral explicitly. And then what we find is this expression over here. There's also this genus counting parameter that we had to fix using some DQFT machinery. But okay, fix this e to the power of s naught parameter, great. Now take this expression for the effective number of degrees of freedom. Now remember that there was a relation between this b parameter and, in principle, L over g Newton. So, which came from like parameterizing the Liouville central charge in this following way, and then taking the central charge as we got it from the canonical quantization. So that tells you that b is of order is something like IL over g Newton or something like that. Plug this into this value of b in here and do a semi-classical expansion. Furthermore, okay, he did it with a logarithm. The square over here you can understand, for example, with the fact that we have two matrices, so we need to have take an effective squared. And then if you do a semi-classical expansion of this expression that we get from the matrix integral, the numbers that it spells out is like pi L is over 2g, which is area over 4g. 3 times logarithm of area over 4g, plus 5 log 2 pi, plus pi I over 2. So the numbers that the matrix integral knows about are the same numbers that the gravitational path integral gave us. So basically this matrix model entropy agrees with the Gibbons-Hawking proposal, which came from a gravitational path integral. Go ahead. You can, in principle, so it's, this tilde here is significant because this tilde could have been slightly different and then it would have given it the opposite sign. So yes. In principle, we have an ambiguity, yes. Right. So that's it. That gets me to my, that's an interesting question. It really comes from here. So, I mean, of course, this thing, viewed simply from a matrix integral perspective, it should be real. It's just counting an effective number of degrees of freedom. It really comes from this consistency of the DQFT that fixed e to the power of s naught to be b inverse. So it really comes from here. And to be really honest here, so this tilde is really significant. So we could only fix this up to some constant numbers. So maybe in the end, we were too quick. The interesting thing was that, I don't know, still, it gave a face if you were, ignoring these constant factors. Very good. So as a summary, and I think I'm really out of time, kind of, yeah. So we had this relation between integrated cosmological correlators and the double-scaled matrix integral. This wave function was then, the wave function we looked at was some expanding spacetime. And we saw that log n effective squared, which is the number of effective degrees of freedom in the matrix integral, reproduced the Gibbons-Hawking de Sitter entropy. I'm really out of time, or am I kind of out of time?
A few seconds.
Okay. So there are some open questions. For example, so far the Hilbert space that we looked at is an infinite dimensional Hilbert space. So it would be very interesting to know, is there some normalizable basis? Is this Hilbert space finite dimensional, infinite dimensional? What is it? I only looked at the sphere. There's lens spaces. What are lens spaces? What is the role of lens spaces in the matrix integral? What happens if you add an observer? Can we put more supersymmetry? Is the supersymmetry, for example, lifting this eigenvalue distribution already? Is that the savior? So is supersymmetry the savior here for us after all? There's a bunch of more questions, but I'll leave it at this. Thank you so much.
Thank you for your talk. We have time for a few questions. Yeah, Kolja first.
So the fact that density become negative, that means there is no consistent large n limit of this matrix model, or the true saddle point has multiple cuts, or what's going on?
There's not a unique completion, because you could deform the eigenvalue distribution in whatever way you want.
But like matrix integral, is it defined as an integral?
Yes.
So there should be a large n limit of
yes, there should be some way. Defined. Yes,
there should be a saddle point which counted. Should be saddle point of the root distribution, which corresponds to a true large n limit of the matrix integral if it's well defined, and it cannot be negative, right? And
no, exactly. So like the fact that it becomes negative has to be cured somehow. Yeah.
So it should be multi-cut distribution of the true saddle point, then, or something like that, like two-cut, like not to single support.
No. Yes, there's definitely more. Yeah, multi-cut. Yeah.
Certain point, you wrote down the spectral curve for starting your recursion relation. Is this spectral curve somehow related to some kind of two-dimensional dilaton gravity, like in JT, or something that you derive from nowhere?
We derived this spectral curve from scratch, imposing the. So basically, we started with the string theory. We calculated AGN for like some low G and N. Also using some technique that's called higher equations of motion, and basically because lower theory is solved, we knew exactly what poles, what zeros, what everything like had to be, and so that's how we got our x of z, y of z. There is a spectral curve of JT gravity, which is like x of z is equal to z squared, and then y of z is some sign. And basically, the reason that we can never transform this into like z squared is the reason why this is a two-matrix integral. So. The one thing that I can say, for example, is that if there are experts in the room, that they might have seen this spectral curve before, because if B is of the form square root of P over Q, this is the spectral curve of an arbitrary PQ minimal string, which is very interesting. But of course, because in the PQ minimal string, the B is like the form P over square root of P over Q, the properties of the spectral curve are very different. So, but yeah, so like this is, yeah. I think this is all I have to say.
Yes, understand.
But we kind of experimentally backwards engineered a spectral curve that satisfied the properties.
About halfway through your talk, you had this sum over genus. So you had this factor G string here.
Yeah.
What do you mean by G string in this model?
I mean, G string is related to it's some genus counting parameter.
So okay, so it's not e to some in the.
No, well, it's related to G string inverse squared is related to like this e to the power of 2s naught, and so s naught is the leading piece in the gravitational path integral. So NC S2B is some constant that we fixed using the 3-point function. I think I confused you more than I helped you, right?
That's okay. Okay. Thanks.
You can fix G string in principle using some TQFT machinery.
All right. One final question.
Hi. Very interesting, of course, this observation. And I have many questions because I know so well this.
There's a long break. Happy to help.
Never noticed something like that. My question is, at some particular G, in principle, you obtain usually the C equals 1 matrix model, matrix quantum mechanics, etc. Do you have this value here?
That would be incredibly interesting. It's still a really interesting question that we don't understand how the C equal to 1 matrix integral in matrix quantum mechanics pops up. We don't know. This is always a matrix integral.
Because there you have access to effective action, that's Javidsky action, so you might have then the real de Sitter picture.
Yeah. It would even be incredibly interesting, like all of this matrix integral machinery, like all of these matrix integrals, they really use topological recursion. It would, for example, also be incredibly interesting to see if there's a topological recursion for the C equal to 1 matrix integral. Sorry, for the C equal to 1 matrix quantum mechanics. So, but we just don't know, like why is C equal to 1 so different? So why is that suddenly a matrix quantum mechanics and not the matrix integral anymore? So I don't know.
And another natural question, do you have here some way to the double scaling limit, sum over genera, etc., like we usually do in.
I mean, in principle, like our matrix integral from the get-go is double scaled. I always consider
scale what essentially you get classical algebraic curve, but I mean there is a standard way for minimal models, etc., to which leads to Pendever-1 equation, etc. The summing up over all the genera. Do you have something like that here?
No. Like, I don't think I have like some Pendever type equation. I mean, maybe I could get it, but I don't know.
Thank you.
Okay, then let's thank Beatrix again. And we meet again after the coffee break.